Second half of tonight's video is about weight. So the weight, or FG, as we'll use in my class, there are a lot of different notations for this, by the way. Sometimes weight is labeled W, sometimes it's simply labeled F. However, the AP exam uses W and F for other things, and so in my class we will call weight F subscript G. Anyway, definition, which you should definitely know. The weight, Fg, of an object on Earth's surface is the gravitational force exerted on it by the Earth. So, everything that has mass causes gravity. And Earth has a lot of mass. So if you've got something near Earth's surface, the Earth pulls down on that thing with gravity. So the force of the Earth pulling down on that thing is Fg, force of gravity. So at this point you might be wondering, what's the difference between mass and weight? Well, in this equation that we're going to be using in tonight's video, weight Fg and mass m are clearly different things. So let's talk about what they are. Mass is how much stuff something has in it. It's not dependent on where the thing is, it's just how much stuff something has in it. Or how much matter. But stuff is actually a good word. How much matter or stuff something has in it. Weight is how much gravity pulls on an object. Object. Weight is how much gravity pulls on an object. And these two things are related. The more mass something has, the more weight it has whenever there's gravity. But if there's no gravity, so let's assume that gravity goes away, if we get rid of gravity, there is still mass, because gravity does not affect how much something has in it. But if we get rid of gravity, there's no longer weight. Weight requires there to be gravity. Okay, so let's take these concepts and try some problems. First example. What is the weight of a 5 kilogram apple on the surface of the Earth? So we're going to use the equation for weight, since this question asks us for weight. Weight equals mass times acceleration due to gravity. Our mass is 5 kilograms. And on Earth, the acceleration of gravity is 9.81 meters per second squared. However, for solving these problems, I'm instead going to say that gravity is 9.81 newtons per kilogram. Newtons per kilogram are the same thing as meters per second squared, and as we talk more about forces, that will become more clear. But for now, we just accept, until we go over it, that the units newtons per kilogram are the same as meters per second squared. And I did this because when I multiply 9.81 newtons per kilogram by 5 kilograms, the units will work out and I'll get newtons, which are the units for force. However, if I don't change meters per second squared to newtons per kilogram, the units don't work out. Alright, here we go. Weight equals mass times gravity. And since the equation is already solved for weight, we can just sub in 5 kilograms times 9.81 newtons per kilogram. And for convenience, we can always approximate with 10 as gravity instead of 9.81. So gravity is about 10 newtons per kilogram. 10 newtons per kilogram, which is 50 kilograms. Whoa, not 50 kilograms. Look what I did there. Messed up my units. So what should have happened, kilograms cancel with kilograms and we get newtons. So the weight of a 5 kilogram apple is 50 newtons. Ready for the next example on the next slide. Next example. What is the mass of a person that has a weight of 650 newtons on Earth? This question is once again about weight, so we'll use weight equals mass times gravity. And as I told you last time, let's go ahead and approximate gravity to be 10 newtons per kilogram. So we know the weight is 650 newtons, and we're looking for the mass. So let's solve the equation Fg equals mg for mass. It will be important to note that Fg is not F times g. Fg is the symbol for weight. So the g is not a separate variable. Fg is one thing. So now I'm going to solve for mass by dividing both sides by g. And I get Fg, or weight, divided by g equals mass. And now if we substitute in 650 newtons divided by 10 newtons per kilogram gives me 65 kilograms. That is the mass of someone that has a weight of 650 newtons on Earth. And by the way, I don't think I mentioned on the last slide, N is for newtons, which are the metric unit for force. All right, last example, next slide. Final example, what is the weight of a 12 kilogram ape on the moon? So we're still using the equation for weight since this question asks about weight. Weight equals mass times gravity. On the moon though, so this could be a problem because the g we know, g is about 10 newtons per kilogram. That g applies only on Earth. So let's look to the problem to see if we can find something else out, where the acceleration of gravity is 1.63 meters per second squared. So on the moon, since we're not using Earth, g on the moon is 1.63 meters per second squared, or, remember I said newtons per kilogram are the same as meters per second squared, 1.63 newtons per kilogram. And again, that unit change is so that we end up with newtons and kilograms at the end of the problem, because that's what mass and force are in. All right, here we go. Let's solve the problem. We have our equation, weight equals mass times gravity. The problem asks for weight, so the equation's already in the right form. We just have to sub in Fg equals 12 kilograms times 1.63 newtons per kilogram, and we get 19.56 newtons. All right, that's it. See you tomorrow.